Welcome! In this video, we'll dive into LeetCode problem number 1592, rearrange spaces between words. This interesting string manipulation problem challenges us to redistribute spaces between words in a given input string. Stick around to learn more about the optimal approach to solve it. This problem is about rearranging spaces in a given string, text. The string consists of words, which are sequences of non-space characters, and spaces, which are represented by single space characters. You are guaranteed that the input string will contain at least one word. The task is to redistribute the spaces between the words so that they are as evenly distributed as possible. If there are any leftover spaces after distributing them evenly, those extra spaces must be placed at the end of the string. The goal is to return the resulting string where the spaces are distributed according to these rules. For example, let's look at the first input. The string text is given as "this is a test." This string contains 9 spaces and 4 words, "this is a" and "test." To distribute the spaces, we calculate that there are 3 gaps between these 4 words, and 9 spaces divided among these 3 gaps results in 3 spaces per gap. Therefore, the output is "this is a test," where the spaces are evenly distributed between the words. Another example is the input "practice makes perfect." Here, the string has 7 spaces in 3 words, practice, makes, and perfect. In this case, there are 2 gaps between the 3 words, and distributing 7 spaces evenly across these 2 gaps gives 3 spaces per gap, with 1 space left over. The leftover space is placed at the end of the string, resulting in "practice makes perfect." On the other hand, if the input is simply "hello," the string contains no spaces and only 1 word. Since there are no spaces to rearrange, the output is just "hello." This problem also comes with a few constraints and edge cases to consider. The length of the input string will always be between 1 and 100 characters, and it will always include at least 1 word. For edge cases, if the string contains only 1 word, such as "hello," no spaces need to be redistributed, and the word is returned as is. If there are leftover spaces after redistribution, they should be appended to the end of the output string, like in the example word 1 word 2, which results in word 1 word 2. Finally, if the spaces divide evenly between the gaps, such as in ABC, no spaces will be left over, and the words will remain evenly spaced. To tackle the problem of rearranging spaces between words, we first need a clear understanding of the task. The goal is to take the given string, count the spaces, and redistribute them evenly between the words, leaving any extra spaces at the end. A straightforward approach to this is brute force. Here, we start by counting the total number of spaces in the string. Next, we split the string into words using a method like Python split. This gives us an easy way to separate the words from the spaces. Once we have the words, we calculate how many spaces should go between each pair of words and how many will be left over. Finally, we rebuild the string by inserting the calculated spaces between words and appending any leftovers at the end. While this approach is intuitive and performs well at O(n) complexity, it does require careful attention to edge cases, such as when there's only 1 word or strings with trailing spaces, which can make the implementation slightly tricky. Now, let's refine our strategy with an optimized approach. This method leverages Python's built-in string functions to make the solution more concise and robust. First, we count the spaces in the string by iterating over it character by character. Then, we use split to extract the words, which has the added benefit of automatically handling multiple spaces. From here, we compute 2 key values: the number of spaces to distribute evenly between the gaps and the leftover spaces. If there is more than 1 word, the spaces per gap are calculated as total_spaces / len words 1, and the remainder is total_spaces %len words 1. Finally, we use join to efficiently insert the calculated spaces between the words and append the remaining spaces at the end. This approach maintains an O(n) complexity while being cleaner and less error-prone than brute force, as it avoids manual string manipulation and handles edge cases naturally. An alternative approach involves manually parsing the string, which eliminates reliance on built-in methods like split. Here, we traverse the string character by character, building words manually while counting spaces. Once we have the words and the total space count, the redistribution logic remains the same: calculate the spaces per gap and any leftovers, then reconstruct the string. While this method achieves the same O(n) complexity, it introduces unnecessary complexity to the implementation. By reinventing basic functionalities like word extraction, we increase the chances of introducing bugs and make the code harder to read and maintain. Therefore, while it's a valid option, manual parsing is less practical compared to leveraging the built-in tools available in Python. The optimized approach is the clear choice for solving this problem. It strikes a balance between simplicity, efficiency, and clarity by leveraging Python's built-in methods like split and join. These methods naturally handle edge cases, such as strings with only one word, where all spaces must be appended to the end. For example, if there's only one word, the length of the words list will be 1, making it easy to detect this case and avoid unnecessary calculations. Additionally, the optimized approach simplifies the redistribution process, reducing the need for manual string manipulation. Compared to brute force, it avoids redundant operations, and unlike manual parsing, it doesn't involve recreating basic string processing functionality. This makes the optimized approach not only cleaner but also more robust. Finally, let's analyze the complexity of the optimized solution. The overall time complexity is O(n), where n is the length of the input string. This efficiency comes from the fact that each step, counting spaces, splitting the string into words, and reconstructing the output requires at most one pass through the string. Since no operation involves nested loops or reprocessing the same characters, this is the most efficient solution possible under the given constraints. By keeping all operations linear, the optimized approach ensures that it performs well even for large inputs, making it the ideal choice for this problem. To solve this problem, we need to redistribute the spaces in a given string as evenly as possible between the words, and place any leftover spaces at the end. The first step in our algorithm is to parse the input string. We start by extracting the words using the split function, which breaks the string into individual words based on spaces. Importantly, this function automatically ignores extra spaces, such as leading, trailing, or multiple consecutive spaces. For example, if the input string is "this is a test," calling text.split will give us the list "this is a test." Next, we count the total spaces in the string using the count method. This count will allow us to determine how many spaces need to be redistributed. In the same example, the total number of spaces in "this is a test" is 9. These two steps, extracting words and counting spaces, form the foundation for the space redistribution process. Now that we have the words and the total number of spaces, the next step is to calculate how the spaces should be distributed. First, we determine the number of words by finding the length of the list obtained earlier. For instance, the list "this is a test" has 4 words. If there's only one word in the string, the problem is simplified: all the spaces are appended to the end of that single word. For example, if the input is hello, there's only one word, so the output is simply hello. For cases with more than one word, we calculate 2 key values, spaces underscore between and extra underscore spaces. The spaces underscore between is the number of spaces that can be evenly distributed between each pair of words, calculated as the integer division of total spaces by number underscore words, 1. The extra underscore spaces are the leftover spaces, found using the modulo operation. As an example, with 9 spaces and 4 words, the division gives spaces underscore between equals 3 and extra underscore spaces equals 0. These calculations ensure that the spaces are distributed as evenly as possible, with any remaining spaces set aside for later. After calculating the space distribution, the next step is to actually redistribute the spaces and construct the final string. To do this, we use the join function, which allows us to concatenate the words with a specific separator, in this case, a string of spaces underscore between spaces. For example, if spaces underscore between is 3, joining the words "this is a test" with 3 spaces results in the string "this is a test." Once the words are joined, we append the extra underscore spaces to the end of the string. For instance, if extra underscore spaces is 2, we simply add 2 spaces to the end, yielding "this is a test." Finally, we return this fully constructed string as the result. This approach ensures that the spaces are redistributed correctly, and any extra spaces are handled seamlessly. By breaking the problem into these manageable steps, we can guarantee accuracy while keeping the implementation clean and efficient. Finally, let's examine the complexity and walk through an example of the algorithm. The time complexity is O, n, where n is the length of the input string. This is because splitting the string and joining the words are both linear operations. The space complexity is O, m, where m is the number of words in the string, as the list of words is stored temporarily in memory. For a concrete example, consider the input string "this is a test." First, we extract the words as "this is a test" and count 9 spaces. Then, we calculate spaces underscore between equals 3 and extra underscore spaces equals 0. Joining the words with 3 spaces gives "this is a test," and since there are no extra spaces, the result remains "this is a test." For an edge case like hello, extracting words gives "hello" and 6 spaces. Since there's only one word, all spaces are appended to the end, resulting in hello. This step-by-step walkthrough highlights how the algorithm efficiently handles both typical and edge cases. This solution addresses the problem of redistributing spaces in the input string such that the spaces are as evenly distributed as possible between words, with remaining spaces added to the end of the string. The code starts by counting the total number of spaces in the input string using the count method. This count helps determine how the spaces will be redistributed. Next, the string is split into individual words using the split method, which automatically removes all spaces between the words. If the input contains only one word, all spaces are appended to the end of the word, and the result is returned. This is handled as a special case since there are no spaces to distribute between multiple words. In the general case, where there are multiple words, the code calculates 2 values: the number of spaces to be placed between each pair of words, spaces underscore between, and the number of leftover spaces, extra underscore spaces. The spaces underscore between is obtained by performing integer division of the total spaces by the number of gaps, which is 1 less than the number of words, while the extra underscore spaces is calculated as the remainder of this division. The words are then joined together using the calculated spaces underscore between as the separator. Any leftover spaces are appended to the end of the resulting string. This ensures that the spaces are distributed as evenly as possible, with any surplus spaces added to the end of the string as required. The resulting string is then returned as the final output, completing the task of rearranging spaces per the problem's requirements. Here, we begin by importing the necessary packages and defining a class called solution. Within the reorder spaces method, the first step is to count the total number of spaces in the provided text. We achieve this by iterating through each character in the text, checking if it's a space, and incrementing the total spaces counter accordingly. Next, we split the text into an array of words using the trim and split methods, where \s+ ensures that multiple spaces are treated as a single delimiter. This provides us with only the words, stripped of all spaces. We then calculate the total number of words using the length of this array. If there's only one word, we handle this special case by appending all of the counted spaces to the single word and returning the result. However, if there are multiple words, we proceed to calculate the number of spaces to distribute between words and the leftover spaces that will remain unallocated. The spaces between variable is calculated by dividing total spaces by the number of gaps, which is word count -1, while extra spaces stores the remainder of this division. Finally, we start constructing the result by joining the words with the evenly distributed spaces using string.join, where the number of spaces is repeated as required. Once the main portion of the result string is constructed, we handle the remaining spaces. These extra spaces are added to the end of the result using the repeat method to append the appropriate number of spaces. Finally, we return the result, which is the rearranged text with spaces distributed as specified. This approach ensures that all spaces are either evenly distributed between words or correctly appended at the end when extra spaces remain. The implementation is both efficient and easy to follow, leveraging basic string and array operations to achieve the desired formatting. Here, we start with an example where the input string contains spaces that are evenly divisible. The input string is "this is a test," and the first step is to count the total number of spaces. By examining the string, we find there are 9 spaces, so we store this in the variable total underscore spaces. Next, we split the string into words using Python split function, which removes all spaces and gives us the list, "this is a test." With the words extracted, we calculate how to distribute the spaces. Since there are 4 words, there are 3 gaps between them. We divide the total spaces by the number of gaps to get 3 spaces between each word. Any leftover spaces are computed using the remainder of this division, which in this case is 0. Finally, we join the words using 3 spaces between them, resulting in "this is a test." Since there are no extra spaces, the final output remains the same, "this is a test." Now, we consider an example where the input string contains only one word. The input is hello, and the first step is to count the total spaces. Here, there are 4 spaces in the input, so total underscore spaces is set to 4. Next, we split the string into words using the split function, which gives us the list, hello. Since there is only one word, we don't need to calculate spaces between words. Instead, all the spaces are appended to the end of the word. By concatenating hello with the 4 spaces, the result becomes hello. This ensures the formatting is preserved even when there's just one word in the input string. In this example, the input string contains spaces that are not evenly divisible. The input string is "practice makes perfect." First, we count the total spaces, which comes out to 7. Then, we split the string into words using the split function, resulting in the list, "practice makes perfect." With 3 words, there are 2 gaps between them. To determine the distribution of spaces, we divide the total spaces by the number of gaps. This gives us 3 spaces between each pair of words. The remainder of the division, which is 1, represents the extra space that will be added at the end. We then join the words with 3 spaces between them, giving us "practice makes perfect." Finally, we append the extra space at the end, resulting in the final string "practice makes perfect." From these examples, we can extract some key observations about how the solution works. First, we always start by counting the total number of spaces, as this determines how they are distributed. The words are split using Python's split function, which effectively removes all spaces and provides just the words. If the input contains only one word, all the spaces are appended to the end of that word. Otherwise, the spaces are divided evenly between the words, and any leftover spaces are added at the very end. The join method is a crucial part of the solution, as it allows us to combine the words with the calculated number of spaces between them. With these steps, the solution handles all edge cases, such as a single word or uneven distribution of spaces, ensuring the output always aligns with the problem requirements. The time complexity of our solution is determined by analyzing the key steps involved in the process. First, counting spaces using text.count requires scanning through the entire string, which takes n time, where n is the length of the input string. Next, splitting the text into words using text.split also traverses the entire string to identify and separate words, making this operation n as well. Finally, the calculations for spaces between words and extra spaces, like total underscore spaces / len words 1 and total underscore spaces %len words 1, are simple arithmetic operations that execute in constant time, or O1. These steps give us a clear idea of the computational cost associated with the initial parts of the solution. Joining the words with spaces is another key step in this solution. The operation *spaces underscore between .join words combines the words into a single string, inserting the calculated spaces between them. This involves iterating through the list of words and constructing the final result string. The time required for this operation depends on the length of the resulting string, which is proportional to the length of the input string n. Consequently, this step also takes n time. When combining all these steps, the overall time complexity of the solution is dominated by the count, split, and join operations, each of which is n. Therefore, the total time complexity is n. Now, let's analyze the space complexity. The text.split operation creates a list to store the words extracted from the input string. In the worst case, if the string has no spaces, this list will contain a single element and require n space. In the best case, even with minimal content, the slicing and storage operations still require n space. Intermediate variables like total underscore spaces, spaces underscore between, and extra underscore spaces are integers and collectively require only 1 space. However, the join operation constructs a new string whose length is proportional to the input string n, consuming n space as well. Summing these factors, the overall space complexity is n primarily due to the space needed for the words list and the final result string. Let's compare this optimized approach to a brute force method. A naive approach might involve manually iterating over the string, extracting words, counting spaces, and constructing the result string character by character. While this would still result in O(n) time complexity, the constant factor would likely be higher due to repeated and less efficient operations. On the other hand, the optimized approach leverages Python's built-in methods like count, split, and join, which are specifically designed for efficient string manipulation. This eliminates redundant operations and ensures that the solution remains both concise and fast. Finally, let's break down the best, average, and worst-case scenarios for this solution. In the best case, where the input string contains only one word, the split operation produces a single element list, and the result string is constructed by simply appending spaces. Even so, operations like count and split still traverse the entire string, maintaining a time complexity of O(n). In the average case, with multiple words and spaces, the count, split, and join operations are all performed, each contributing O(n) time. In the worst case, if the input is entirely spaces, split returns an empty list, but the operations still require O(n) time to complete. Across all cases, the time complexity remains O(n), and the space complexity also consistently stays at O(n). When tackling this problem, there are a few common mistakes to watch out for. First, overlooking edge cases like a single word in the input string can lead to incorrect results. For instance, if the input is just one word surrounded by spaces, all those spaces should shift to the end. Missing this detail can cause your output to fail edge case testing. Next, miscounting the total number of spaces is another pitfall. This often happens if you rely solely on splitting strings without explicitly accounting for every space in the input. Always count spaces directly to avoid errors. Additionally, improper handling of leftover spaces can disrupt your solution. If the spaces don't distribute evenly between words, any extras must be appended to the end of the output string. Lastly, inefficient string operations, such as using concatenation and loops, can significantly slow down your code. Instead, leverage the join method to construct strings more efficiently and maintain a linear time complexity. Another common issue is splitting words incorrectly. Using the split method without arguments removes all extra spaces, which can disrupt the original space structure. This is why it's crucial to use split carefully and verify its behavior with test cases. From an interview perspective, this problem is designed to assess your ability to manipulate strings efficiently while handling edge cases. Always start by clarifying edge scenarios with your interviewer, such as whether the input could contain special characters or only valid words and spaces. This problem also tests your ability to recognize patterns, particularly splitting, counting, and redistributing components in strings, an essential skill for numerous string manipulation challenges. To optimize your solution, focus on minimizing inefficiencies by using join and pre-computing values like the total spaces and the number of words. Remember that asking clarifying questions early can save you time and help you avoid incorrect assumptions about the input. This problem connects to several similar challenges on LeetCode, making it a great stepping stone for more advanced string manipulation tasks. For example, LeetCode number 68, text justification, is a more complex variation that involves justifying text into multiple lines while maintaining proper alignment. Then there's LeetCode number 151, reverse words in a string, which emphasizes rearranging words and spaces within a string. A related problem, LeetCode number 186, reverse words in a string 2, adds the requirement of in-place modification, making it slightly more challenging. Finally, LeetCode number 58, length of last word, focuses on parsing strings to extract specific components, such as identifying the last word in a given input. These problems all share common themes of splitting, rearranging, and reconstructing string data, so practicing them can improve your proficiency in handling similar tasks. When approaching this problem, there are a few different strategies to consider. A brute force approach involves splitting the string into words and spaces, then manually redistributing the spaces. While this method is straightforward and easy to implement, it can be inefficient due to repeated string operations like concatenation, which can degrade performance. On the other hand, an optimized approach leverages Python's join method. Here, you would split the input to extract words, count the total spaces, and compute how many spaces go between words and how many are left over. This allows you to efficiently reassemble the string while handling edge cases gracefully. Another alternative involves using data structures like lists to separately store words and spaces before reassembling the output. While this method may be slightly more verbose, it can simplify debugging and make the logic more explicit. Each of these approaches has trade-offs, so choose one based on the problem's constraints and your familiarity with the techniques. Understanding the complexity of your solution is critical, especially when discussing it in interviews. For this problem, the time complexity is O(n), where n is the length of the input string. This is because you process the string linearly, counting spaces and splitting words in a single pass. The space complexity is also O(n), as you temporarily store the words and spaces extracted from the input before reassembling the output. These complexities ensure that your solution is efficient and scalable, making it suitable for handling large inputs. Aim to achieve this optimal complexity by avoiding redundant operations and leveraging efficient methods like join-for-string construction. By keeping your solution both time and space efficient, you demonstrate a clear understanding of algorithmic design principles. Great job! To recap, we solved the problem by dividing it into manageable steps, splitting words, redistributing spaces, and reconstructing the result. Remember to apply these techniques to similar problems and keep practicing. Thank you for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!